All right. So what I'm going to do now is do the notes on the mole, but we're only going to cover about half of the pre-notes that you already have copied down. We'll finish those notes on Monday. Oh, I'm not presenting my screen. Mr. Massey, you're not presenting your screen. Okay, Unit 5, the mole. Now, the term mole comes from a German word meaning molecular mass, but we use the term mole. Okay, now before we get into it, just a reminder that when we talk about substances like sugar or water or sodium chloride or iron metal, well, the particles that make up those substances are different. And so it's just a quick little review on what those particles are. If you have an element like copper, well, it's composed of monatomic atoms, just individual atoms. So if I had a sample of copper, it's made up of copper atoms. Ions has a positive charge on it. If you had a sample of ions, that would be the particles. Molecules, like water, if you had a glass of water, well, it's composed of water molecules. That would be the particles. If you had sodium chloride, well, that's what we refer to that as a formula unit. Now, the term formula unit, I know it's kind of a clumsy, awkward word, but it's important that you distinguish it from an ionic compound from a molecule. Remember, a formula unit, an ionic compound, forms a crystal lattice, where it's the formula unit tells you the ratio of ions in the crystal lattice. And for sodium chloride, it's a 1-to-1 sodium and chlorine. So the term particle encompasses all of these. Just like if I say humans, well, that encompasses all of us. Though there's those boys and girls and whatever in between or outside of that, older people, younger people. So you can classify different people in different ways. In the same way here, you can classify particles in different ways. Now, that term particle will be a holistic, a general term that we'll be using shortly. Okay, the mole. 1 mole, and the abbreviation that's pretty much universally used, is MOL. Please don't reduce it down to M. Remember, that means meters. Is the amount of a pure substance that contains 6.02 times 10 to the 23rd. And so we're using this term particle until we can be more specific about a particular substance that we're talking about. In honor of the first scientist to calculate its value, this number is called Avogadro's number, after Amedeo Avogadro. He was the first person to measure this. He did it using gases. And what he did was he took a sample of gas, and how this is done, and there's many different ways to arrive at that number, 6.02 times 10 to the 23rd. And the way Avogadro did this was really quite remarkable for the time. This was a few hundred years ago. It's a bit beyond our scope right now, but nonetheless, he was able to count the number of atoms that were in a sample. And from that, we arrive at this number for what's called 1 mole. Now, just in the same way as a dozen means 12, so if I had a dozen donuts, it'd be 12 donuts. That's exactly the same thing that a mole means, except the number is different. The number is 6.02 times 10 to the 23rd. Now, that is an enormous number. It's beyond really our ability to comprehend how huge that number is. So I'll give you an example here. If you had a mole of marbles, it would cover the Earth to the depth of 3 miles. Just a crazy large number. But let me give you another little visual here. I have some green water. I just put some food coloring in it. And I'm going to pour in this beaker about 18 milliliters of water, which is 18 grams of water. And that is 1 mole of water, which should give you pause that you have that many molecules in here. Imagine this. If each one of these molecules in here, 1 mole, 6.02 times 10 to the 23rd molecules of water, if each one was magically able to expand to the size of a basketball, it would occupy a volume the size of planet Earth. So that should give you both a sense of how enormous a mole is and also some appreciation for how incredibly small atoms and molecules are. Most people kind of think they have a sense of how small an atom is, and usually it goes along the lines of if you were to take like a little grain of sand, say, and maybe with a magnifying glass and kind of pulverize it with a hammer, and that tiny little dust particles that you would get, people kind of have the idea that that approximates the size of an atom or a molecule. You are mountains away from how incredibly small an atom or a molecule is. Most of us at some point in time have grasped, usually in our childhood sometime, grasp the concept of infinity, what infinity is, just go on and on forever. We can understand the concept, but we really can't visualize what infinity would be. Our feeble minds just can't wrap our wits around that. Likewise, when we talk about how small an atom is or how small a molecule is, which is infinitesimally small, we also can't quite grasp that degree of smallness. But nonetheless, we are able to count how many we would have in a certain mass. And it's called the mole. So again, just a little analogy here. If we say a pair, well, that would mean 2. We said a dozen, well, that would be 12. In exactly the same way, if we say a mole, it means 6.02 times 10 to the 23rd. Now, writing it in scientific notation often is a bit deceptive, so it's a good idea to keep in mind on how it would be written in standard notation. That's 21 zeros after the 602. So it's a huge number. Okay, now the key idea for our purposes is that the mole, for the mole, the atomic mass of an element will always be in grams, not AMUs. And you may have forgotten AMUs. We learned this in our first unit. AMU stands for atomic mass unit. And it's defined to be 1/12 the mass of the carbon-12 isotope. Some of you might remember that. And the reason carbon-12 isotope is because it has exactly 6 protons and 6 neutrons. So if we take the mass of that atom and divide it by 12, we would have the mass halfway between a proton and a neutron, and that's the definition of an AMU. But, and this is the whole beauty of the mole, is that we can, rather than having the unit be AMU, if we simply convert that unit to grams, well, then that means that for every element's atomic mass, and the atomic mass is the number that has decimal places, if we had that mass of an element, we would have 1 mole of that element. So if I had 1.01 grams of hydrogen, it means I would have 6.02 times 10 to the 23rd hydrogen atoms. The same thing for nitrogen. But for nitrogen, it would be 14.01 grams because nitrogen is a bigger atom. So if you have a mole of them, it'll have a greater mass. But this is an enormous step, was an enormous step forward in chemistry to be able to do analytical chemistry, to take measurements of substances in the real world and convert that into actual number of particles that we would have. So this is if you have 1.01 grams of hydrogen, that's 1 mole of hydrogen. If you have 14.01 grams of nitrogen, you would have 1 mole of nitrogen. Now, of course, the masses are different because the atoms are different. It would be like if you had a dozen ping pong balls compared to a dozen bowling balls. You'd have the same number, but the bowling balls would be much more massive. Now, it's going to be really important that you have your periodic table available. So if you don't have it right now, I'll run and get it. I'll wait like 5 seconds. Now remember, we need to use this periodic table because the atomic mass, the numbers that have decimal places, can be different on different periodic tables. Some publishers have more or less decimal places, and some even round a bit differently. So for all of our calculations to agree, we need to have the same reference table. So make sure that you use this one. Still available for pickup here at Tigard High. All right. Okay, now this little flowchart will be really helpful to do the math that we're about to do. So what you see here is that we can convert mass to the number of moles, and we can convert moles into the number of particles. Now the term particles is generic, but we'll replace that term with either atoms, ions, molecules, or formula units when we know what it is we're talking about. Now for each one of these conversions, we're going to do something that's exactly like dimensional analysis. Remember, all that math stuff that we did, there was a purpose for it. We're now going to employ all of those math skills that you have developed in the past week. To convert mass to moles or moles to mass, we need to have a relationship between the two. Just like 12 inches is equal to a foot, we need a relationship. For mass and moles, it depends completely upon the element that you're talking about. So it would be the mass, and we refer to that as the molar mass of, and we'll be talking about an element, so it'll be the atomic mass of an element from the periodic table, and that would be the mass per mole. So that would be the relationship. Now, we can't be specific here because it's specific, the mass is specific to a particular element. We would have to look up the atomic mass of the element. But once we know what the element is we're talking about, that's what would go there, grams. Now remember, once you have a relationship between two things, you can come up with two conversion factors. Each is the reciprocal of the other. So that's what we have down here. So you could have the atomic mass of an element per mole, or 1 mole per the atomic mass of an element. We'll choose the one, just like we did with dimensional analysis, such that the units will cancel out. Remember, that's the whole beauty of dimensional analysis, is that just paying attention to the units, things cancel out. Now, if we wanted to convert from moles to the number of particles or back again, we only need Avogadro's number, which is 1 mole is 6.02 times 10 to the 23rd particles. So from that, we can have these two conversion factors, 1 mole over Avogadro's number or Avogadro's number over 1 mole. Okay, now I'm going to come back to this flowchart as we go through. Actually, I'm recording this for some people that are absent, so it's going to be difficult for me to come back to that. You might want to take a screenshot of it if you don't have it already in your notes, so you can pull it up. But what I'm going to do now, okay, we're going to do some practice problems. Now, I did this on the board. I'm doing this as a separate recording for those of you that were absent. Now, the problems that we're going to be doing, I'm going to give you 3 example problems. We're simply going to be doing these conversions, going from mass to moles, from moles to number of particles. So it's just dimensional analysis, like if I was going from inches to feet to miles or something like that. Now, to do any conversions, we need to know the relationships between the two. And so the relationships are given in these, are given right here, and then we have our conversion factors here. So I'll be coming back to this as we solve the problem. Okay, so the first problem, a gold ring has the mass of 5.11 grams. How many atoms does it contain? Now remember, with all dimensional analysis problems, you always know where to start. You start by writing down what you're given. So we're given 5.11 grams of gold. Now, in order to convert grams to moles, we need to know what the mass is of 1 mole of gold. And for that, we need to go to the periodic table and find gold. Gold is atomic number 79. It has the atomic mass of 196.97. Now, looking up the atomic mass of the elements is something you'll be doing an awful lot of in this unit, so get used to it. So 196.97 grams of gold per mole. And so that's what would go here, 196.97 grams per mole. So that will be our conversion factor. Now we know that grams need to cancel out, so grams goes in the denominator. So it will be, so this would be the conversion factor that we'll use, grams in the denominator. Then we want to convert moles to atoms. And so for that, we'll use this relationship. 1 mole of any substance is 6.02 times 10 to the 23rd. Now we can replace the term particle with atoms because we know what we're talking about here. We're talking about elements. So that'll be the next conversion factor. Moles goes in the denominator so that we can cancel them out. And then we're ready to go. Now to type this into your calculator, it would be 5.11 divided by 196.97 times 6.02 EE23, or times 10 to the 23rd. And you should be getting 1.56 times 10 to the 23rd atoms. Now we need that unit atoms there. We rounded our answer to 3 significant figures because that's what we started with. Remember, we always round to with what we start with. We treat conversion factors as if they were exact relationships. They have infinite significance. Okay, next. How many atoms of carbon are in a 0.25 carat diamond? I don't know if you know that, but diamonds is composed of nothing but carbon atoms. Carbon can combine in various ways. It's referred to as allotropes of carbon, and diamond is one example. Now they give you that 1 carat is 0.20 grams. So we need to first convert the carats to grams before we can go to our little flow chart here, converting mass to moles to particles. So we'll start with that, 0.25 carats, and then this is we'll create our conversion factor. Carats will be in the denominator, so they cancel out. So now we have grams. So now we can convert grams to moles, but we need to know the atomic mass of carbon. And so if we find carbon on the periodic table, it's right here. So its atomic mass is 12.01 grams. And that will go in the denominator because we want grams to cancel out. So again, it's 1 gram is 1 mole. So this is the conversion factor we're using. Moles are in the numerator, grams in the denominator. Next, we want to convert to number of atoms. And so we would use this conversion factor because we want moles to cancel out. So 6.02 times 10 to the 23rd atoms per mole. Again, we want units to cancel out. Again, I know I've said it a couple of times already, but if you just pay attention to the units, everything falls into place. It's really easy to see if you made a mistake. Like if you had this upside down, moles wouldn't cancel. Okay, now when you type this into your calculator, and you can pause the video and give it a shot, but it would be 0.25 times 0.20 divided by 12.01 times 6.02 EE23. And for this one, we need to round our answer to 2 significant figures. So it would be 2.5 times 10 to the 21 atoms. Now don't forget that unit. And every number, notice, has a unit on it. Okay, and then the last one, we're going to be going in the reverse. Instead of being given the mass, or in this case carats, and converting to atoms, we're going to go in the opposite direction. We'll be given atoms. If a balloon contains 1.5 times 10 to the 24 atoms of helium, how many grams of helium is this? All right, so what we'll be doing here is going in the opposite direction. Notice these are two-way arrows. So just like we can convert inches to miles, we can convert miles to inches. So in this case, we're given atoms, and we need to convert it to mass. So the starting point, as always, would be to write down what we're given. 1.5 times 10 to the 24 atoms. And we want atoms to cancel out. So this will be our conversion factor here. 1 mole over 6.02 times 10 to the 23rd atoms. So atoms cancel out. And then we want to convert moles to grams, and that will be this. We need to know the relationship between 1 mole of helium and its mass. So we need to go to the periodic table, find helium. It's over here. Helium's atomic mass is 4.00. And that moles will go in the denominator, so they cancel out, and it'd be 4 grams, 4.00 grams per mole. So again, all I'm doing here is using this conversion factor. 1 mole is 6, I'm sorry, this conversion factor, 4.00 grams per mole. Okay, to type that into your calculator, it'd be 1.5 EE24 divided by 6.02 EE23 times 4. Now this one's a little tricky to round it to the correct number of sig figs. So I challenge you to pause the video, see if you can get the right number of sig figs, and then start it up again. Okay, you're back. All right, so your calculator is going to give you 9.9667, and it goes on and on. But we know that we need to round it to 2 significant figures. So when we do this, we need to get rid of everything after that second 9. So the 6 rounds up, so the 9 becomes 10, and this 9 becomes 10 too. So we need to round that to 10, but it needs to have 2 significant figures. So we need to put a decimal point there. Without that decimal point, you would have only 1 sig fig. Now you could do this in scientific notation, 1.0 times 10 to the 1, but this is an easier way to do it. Okay, now this was the practice that I did on the board. I'm now going to return you to the video that I had recorded during class. It's called Lab How Many Atoms? And it looks like this. Now there's a lot of verbiage here, but the heart of the lab is that you're going to copy this table, just as it says above here, copy this table including the column headings, and I'm going to be giving you the mass of these 6 elements. And you're going to be doing the calculation just as shown in the example to determine how many atoms you have. Now the little warning along the side or along the top of the table is just to ask you to please make sure that you draw your table large enough to do these calculations. Some of you make these tables that are super small, so you have to cram everything in there and write super small. Please don't do that. And you might find rather than having your notebook like this, turning it sideways might be a better way to do this. You have more room. Okay, now you don't need to copy the example down, but it is there to refer to. The title of this is Lab How Many Atoms? And why don't I give you about 3 or 4 minutes to get a start on copying this table down. And, but the only thing you really need from me is the data. So let me give that to you right now. Okay, so I have samples of each one of these elements before me here. And so the first one is copper. And I'm going to be using a pre-1982 copper penny. I don't know if you know, but before 1982, pennies were 100% copper. After that, they became mostly zinc because it was cheaper, but it's still copper coated. But this is pure copper. So the mass is 2.55 grams. So you're going to be converting that to the number of atoms. Okay, the next one, so I'm just going to give you all the masses right now, so make sure you copy this down. The next one is lead, and it's just a piece of lead. It's a very dense metal. It's quite heavy. This is heavier than you might think. This is 54.67 grams. Now note that the copper has 3 significant figures, and so your answer needs to have 3 significant figures. But lead has 4 significant figures, so your answer would have 4 significant figures. So pay attention to that. Okay, the next is carbon, and rather than a diamond, I have charcoal. And if you don't know, if you just take wood and burn it all the way through, that's what we call charcoal, and it's just 100% carbon. So it is 14.96 grams. And then iron, So I'm just going to use a little iron S hook here. 42.15 grams. Then just a piece of zinc, just a zinc foil. $17.77 grams. Now, in class, people are usually here. I ask if somebody has a piece of jewelry. You have any silver? Okay. And usually somebody has a ring or bracelet or something that's silver. Nobody's here. So I have just a piece of silver foil. It's kind of like thick aluminum foil, but it's just a tiny little piece. It's the most expensive of the samples I have here by far. Its mass is 0.32 grams. Notice that it only has two significant figures, so your answer needs to reflect that. All right, that is what you need to do. You have 10 minutes left of class, so why don't I turn you loose on doing this? I'm not saying goodbye, don't leave yet, but I'll give you the remainder of class to work on this assignment. Again, it'll be due Monday, but hopefully you can just get it done right now.